So today we're going to be looking at some structures. We're going to be analyzing them using H NMR. So H NMR is utilized, but what it does is it shows the characteristics of the hydrogens that are in a molecule. So sorry about my writing here already, but we're just going to go back over this. Okay, so there's a couple of things that you want to look at when you're looking at H NMR. So the things that you want to look at are the number of signals, the position of the signals, integration of signals, and spin-spin coupling. So what we're going to do is we're going to start off by looking at the number of signals. So we're looking at the spectrum of 2-propanol, and we can see that there are 2 clear signals here. The way that we can determine that these are 2 separate signals is if we look at the bottom, there's a connection here between these 2 little peaks, and there's a connection at the bottom here between these peaks over here. So that helps us notice that there's 2 signals in the molecule. So the number of signals corresponds to the number of unique hydrogens in a molecule. So that means that these hydrogens are unique from these hydrogens over here. We'll leave it at that for now, and then we're going to look at the position of the signals. So the position of the signals involves looking at the ppm at which the signals arise. So right here, this is at about 1.2 ppm, and if we look on our sheet right here, we see that 1.2 ppm goes about right here. It could be an amine, or an alcohol, or an alkane. So this means that based on the ppm at which this signal is showing up, it could be hydrogens that are a part of any of these 3 functional groups. Now over here, we see that this is at about 3.7 ppm. And if we go up here, we see that it could be an alcohol, an ester, or an ether, or a halide. Ester, ether, or halide. Okay, so next what we're going to look at is the integration of the signals. So the integration, which are these numbers, tells us how many hydrogens are exhibiting that behavior or showing up at that signal. So right here we see that this is 6 hydrogens. So that means that 6 hydrogens are being integrated for by these. 1 hydrogen over here. So that means these 6 hydrogens are all equivalent. This 1 hydrogen is also by itself, but it's also equivalent with itself. So next what we can look at is the spin-spin coupling. So the spin-spin coupling has to do with the number of peaks that we see. So with this, we call it a doublet because there's 2 peaks within the signal. And with this, there's actually 7 peaks if we count them out. And that can be called a septet. So what the doublet and the septet tell us is the number of neighboring hydrogens that these hydrogens have that they are not equivalent to. So a doublet, you do n minus 1. So a doublet minus 1 is 1, so that means that these 6 hydrogens have 1 neighboring hydrogen they are not equivalent to. This hydrogen has 6 neighboring hydrogens that it is not equivalent to. So now, with these 6 hydrogens, if these are all equivalent, we can assume that it's probably 2 methyl groups. And with this hydrogen, we can assume that it could be an alcohol or maybe an aldehyde because it's just 1 hydrogen, but that's not an option based on what we came up with based on the ppm that it's showing up at. So this is likely an alcohol. So right here, we're left with an alcohol as our option. We know it's not going to be an ester or an ether or a halide because if we look at the structure that we're talking about, it's 2-propanol, which looks like this. It's called propanol because it has 3 carbons, all due to the alcohol, and 2 because the alcohol is coming off of the 2nd carbon. So based on that, in our 2-propanol, we have an alcohol, and we also have some methyl groups. Now, this makes sense with the fact that we thought this could be an alcohol. And there can't be an ester, ether, or halide because none of those are present in the molecule. Over here, we had that this could possibly be an amine. That's not possible because there's not a nitrogen. an alcohol, there's only one alcohol in the molecule and it's been taken care of, so we're left with alkane. So we have our CH3 groups and our alcohol. So lastly, we're just going to look back over our molecule, see if it makes sense. This hydrogen is seeing 3 hydrogens here and 3 hydrogens here. So it has 6 neighbors, which makes sense considering we saw a septet right here corresponding to the 1 hydrogen. Additionally, we see right over here that these are 6 hydrogens and that they have 1 neighbor. These 6 hydrogens, 3 and 3, only have the 1 neighbor of the alcohol, the hydrogen coming off of the oxygen. One last thing to mention is the reason that this hydrogen is showing up so much further downfield, so much further towards the left than those other hydrogens is because it is de-shielded by this oxygen. And when something is de-shielded by another atom, it's going to be showing up further downfield. So that we're done with our structure of 2-propanol. Now we're going to move on to a slightly trickier structure, which is going to be the H NMR of aspirin. Again, sorry for the writing already. I did this before and it did not save. Okay, so we're just going to start at the beginning. I've drawn out the structure of aspirin. I'll redraw it to make it more clear. We have a benzene ring. We have a carboxylic acid coming off of it. We also have an ester, coming off of it. Okay, so that is the structure of aspirin. Like I said, this is a carboxylic acid. This is a benzene, which has some alkenes in there. This is an ester. And over here we have a CH3, so a methyl group. Okay. So now we're going to start looking at our structure. So first what we can do is we're going to look at these peaks that we see. So we see a very strong peak around 2.2 ppm. So we want to deduce what that could possibly be corresponding to. If we look on our sheet, we see that 2.2 ppm could be an amine, could be an alcohol, could be a carbonyl, an alkyne, possibly a halide, an alkene / aromatic, and possibly an alkane because it's just a little bit higher than the 2 that has the alkane cut off. Now we want to look at what our other things could be. This one is it's standing out because it's all the way at 11 ppm. Now if we go up, we see that at 11 ppm, pretty much our only option is a carboxylic acid. So that's probably corresponding to the hydrogen of a carboxylic acid, which is right here. If we look between about 7.8 and 8.2 ppm, we want to look at what our options could be. It could be an alkene or an aromatic. So we're going to write that down. So without structures to match to, without being given this structure as well as others and trying to match, coming up with what our molecule is solely based on the H NMR for a molecule this complex is pretty much impossible. So I just want to note that it's important that we're thinking of it in terms of would we be able to match this spectrum to this structure as opposed to could we come up with this structure without seeing this prior. Okay, so we have what our options could be for all of these compounds. Now, what we want to do next is look at how these signals are appearing. So this is appearing as a singlet. It's just one line. We don't see any other lines. These are appearing as, it's really hard to tell, but possibly multiplets. And over here, this is a singlet. So what we know about the singlets is that they're going to have no neighboring hydrogens. They're not going to be coupling with any other hydrogens. So that means that these are probably going to be, the hydrogens corresponding to these singlets are probably going to be next to an oxygen that's shielding them away from the other hydrogens. So this singlet, we have that it could possibly be of an amine, an alcohol, a carbonyl, alkyne, halide, alkene or aromatic, and alkane. So we can automatically throw out the amine and also the alkyne, because if we look at our molecule, we don't see either of those present. We also don't see a halide. So that leaves us with an alcohol, carbonyl, alkene, or an alkane. So another thing we can throw out is that it's an alcohol because there is this OH here, but it's connected to this double bond to O, so it's a carboxylic acid. So it's not an alcohol. Next, we're going to just move on to this peak for now. It's pretty much just an alkene or an aromatic, and if we look at our compound, there's very clearly an aromatic, so we know that this is corresponding to the benzene ring. And right here, it's very clearly the carboxylic acid in our molecule. So far we've determined that there is the carboxylic acid in our molecule, and that peak corresponds to it, and that there is a benzene in our molecule, and that these peaks correspond to the benzene. And over here, what is left in our molecule besides the benzene, besides the carboxylic acid? We do see this ester right here, and we also see this methyl group. Esters don't absorb this low if we look on our chart. So it's not going to be an ester, it is going to be a methyl group. This peak is likely corresponding to this methyl group. So let's talk a bit more about these peaks, because there's a lot going on over here. So these are corresponding to the hydrogens coming off of the benzene ring. This hydrogen, this hydrogen, this hydrogen, and this hydrogen. Up here is our carboxylic acid, and over here is our ester. So these hydrogens are all we would expect them to all show up at different ppms because they're experiencing different effects of the groups surrounding them. For example, this hydrogen is next to a group containing a carboxylic acid and another hydrogen. This hydrogen is next to two hydrogens. This hydrogen is also next to two hydrogens. And then this hydrogen is next to a group with a lot of oxygens and a hydrogen. So if we look at these peaks, we see that they're of different heights. This hydrogen and this hydrogen are smaller in height than is this peak. These hydrogens are likely corresponding to these hydrogens right here, where this peak is probably corresponding to these hydrogens. The reasoning that these hydrogens may be showing up the same, even though if you go out a couple more functional groups, they're experiencing different effects, is because they're close to one another. They're both seeing two hydrogens on either side, and they could just be overlapping. So that is why this is about double the height of that, because it's corresponding to two hydrogens. So if we count, we see that we have a hydrogen accounted for here, 3 hydrogens accounted for here, 4, 5, 6, 7. Oh, sorry, 8. So if we count the number of hydrogens in our molecule, we get 3, 4, 5, 6, 7, 8. So all of our hydrogens are accounted for. So there's just a couple of other things that we want to look at. One of the main things is we see an ester in our molecule, but we don't see an ester where we'd expect it to show up here between 3 and 5.2 ppm right here. So we're wondering why that is. This is likely because there's no hydrogens directly connected to the ester. There's no hydrogens that are experiencing the effect of it. So that is why we're not seeing it show up here, because the H NMR just shows the behavior of the hydrogens. Additionally, you might be thinking that these hydrogens should be showing up in the ester range. However, they are not experiencing the effect of this oxygen as strongly as they would if they were on this side. So they're more likely just experiencing this like carbonyl effect. And if we look, carbonyl compounds are expected to show up between 2 and 3 ppm, and we see a peak at 2.2 ppm. Additionally, we could think of it as these alkane hydrogens, because they're connected to a C, which is connected to another C with a single bond, are just showing up a bit further, more downfield than we would expect, because they're experiencing the de-shielding from the oxygen, which makes them show up further downfield. So with all of that being said, we were able to match all of our hydrogen peaks to our compound, to the structure we were given, and we were able to make sense of why all of the peaks are showing up where they are. So we were able to deduce, based on using the same steps that we used for a simpler molecule, that these hydrogens are corresponding to aspirin.